Example 3. And we are going to spend more time graphing rational functions like examples 2 and 3 as we go throughout this unit. But pause the video and try to graph this. You could use a table of values. Try not to use a calculator. Let's see if you can figure it out. And restart the video when you're ready. This function actually has a horizontal asymptote at y equals 0. Since, oops, this is super weird. Let me just try this again. This function has a horizontal asymptote at y equals 0, since we have a larger degree on the denominator. It also has a vertical asymptote at x equals 0, since there is a domain restriction at 0 from the denominator of this rational function. You may or may not remember some of those details on graphing rational functions. We are going to be reviewing them later. If you plot a couple points on either side of the vertical asymptote, maybe some points like 1 and -1, what you end up with is 4 and 4. I'm going to use these points to just get my sketch, and I'm going to use the bounds from the asymptotes to help me then fill in the curve. And the more experience you get with these, the more you start to anticipate, +4, what these are going to look like. By the way, you might wonder, why does the left and the right side of this appear to be symmetrical? When you square something, you always end up with a positive power. And so what happens here is, regardless if you input negative or positive inputs, if they have the same number but just different signs, and you square them, you're going to keep getting the same output. So that's why the left and the right side here are mirror images. All right, we want to find the limit of this as x approaches 0. So let's take a look at the heights. As I approach 0 from the left, I'm going up larger and larger forever. I'm going up to positive infinity. As I approach 0 from the right-hand side, I'm also going up to positive infinity. And so some people then write that limit as positive infinity. But a limit's supposed to be a specific height. A limit is supposed to be an actual number. And infinity is an idea. It's not a number. It's a concept. It's the idea that after any named number, there's always a larger number, whether it's named or not. And so I'm not going to use infinity as my final answer here. I'm going to say it doesn't approach a specific number, so the limit does not exist. Now, our textbook is going to use infinity. College Board would use does not exist. So, to accommodate that, we're going to use both. We're going to use does not exist and positive infinity because both are descriptives. And I'm requiring, and so is Mr. Gannon, that you write both of those. All right, let's take a look at this next one. This is weird. We haven't seen this before. As x approaches infinity. So what this is asking is what's happening to this graph as I look at larger and larger inputs. Instead of looking at one specific input, they're saying what happens to the height as you move along the x-axis to the right. Well, what's going to happen is we're going to approach this horizontal asymptote. And this horizontal asymptote has a height of 0. So limits to infinity are going to talk about the heights of horizontal asymptotes. So, unbounded behavior, when you're talking about the term unbounded, we're talking about things happening to infinity. So, some conclusions for unbounded behavior is that if a graph's height approaches positive or negative infinity, it could be going up forever or down forever, what we're going to say is that limit does not exist. And we will say like does not exist because it's positive infinity, or does not exist because it's negative infinity. We'll explore that more later on a different lesson. However, if you are asked to find a limit as x approaches infinity, or as x approaches negative infinity for whatever function we're looking at, f or h or whatever, what we're looking at is this is asking you for the height of the horizontal asymptote on that side of the graph. You may not be aware of it. You can actually have more than one horizontal asymptote in the graph. Another thing we'll talk about later. Okay. For this next one, we are going to need to use the calculators. So please take out your Inspires. And I don't know why, but I closed mine. I forgot that this one was on there. So I'm going to have to open up my Inspire. Very exciting while you all get to wait and watch me do that. Might open up faster since I've already used it once today. And please open up yours as well. And what we're going to do is we're going to look at a graph this time. And so your Inspire has the ability to graph things, and so that's what we're going to be looking at eventually. And again, you will eventually really like these calculators, just maybe not quite yet. Okay. So as I work on this, I'm just going to try to get this back to, yours probably doesn't look like this in the beginning. The calculator is a little different on the computer. So you might have something like that, or you might have, if you push the on button, something like this. What we're going to do is we're going to, and that's called the home screen, we're just going to arrow down to graph and choose that. And I'm going to graph the function cosine of 1 over x. Now, this calculator has, to the left of the 7, a button for all your trig functions, even inverse ones and reciprocal ones, really cool. And I'm going to type cosine of 1 over x. And I'm going to graph it. And if you look at this limit graphically, what height are we approaching? You might think, it looks like we're approaching 0. I could see that myself. That's not actually going to be true. And to kind of see that, I, on the directions on your table, told you to change your window, but I think maybe we'll just zoom in a lot. I'm going to go menu. I'm going to go to Windows/zoom and click that option, and a whole bunch of options are going to, I'm just going to zoom in. I'm going to make the center right here. We're trying to see what's happening as x approaches 0. I'm just going to keep clicking right there. You have this little mouse, okay, over here. How weird. You guys see what's happening here? I'm going to keep clicking. And click. In fact, why don't you pause the video and click as many times as you want, and then restart this when you're done. No matter how many times I click this, what's happening is this behavior is going up and down and up and down. In fact, it starts to look like a barcode. We're going to call this oscillating behavior. An oscillating behavior is when the behavior just switches between other two numbers, like 1 and -1, an infinite number of times. So what happens here is that this graph, although when we first looked at it, it didn't seem so bad. It was like, But as we zoom in, this start right here starts to look like a barcode. Up and down and up and down, and it never approaches one specific height. We call that oscillating behavior. And since we're not approaching a specific height here, at whatever value we're looking at, in this case it was 0, we're going to say that that limit does not exist. This is a little pitfall for our technology, because if we're not careful and we don't really look carefully at certain things, we might be fooled. If we had not zoomed in, we might have thought, oh, this limit looks like it approaches a height of 0, but it wasn't actually true. There is a little summary here of what we talked about today for types of limits that don't exist. I'll let you read that on your own, and we are done with the notes. I hope you have a great rest of your day.